So I hope you can see my screen.
Yes, perfect.
Is the size good to read all the stuff, or do I need to zoom in more?
No, I think we can start. Yeah.
Okay, but the size is good, or?
Yes, for me at least
okay.
It's perfect.
Okay, so I hope you can all find or see the link in the chat here. So what you can do is you can go to File and then save a copy in Drive. So you can make your own copy of the file, and then this copy should be editable. So you can change it and play with the code and do it yourself. If there's any problems, please let me know. We also have Patrick Reiser here in the call. So you can also send messages to him if you have any questions while I'm talking. So he can also help you out if something is not working properly. Sometimes I already say now, if you run into some NumPy error, we don't really understand why it happens in Google Colab. But what always helps is if you do just runtime and then restart runtime, then this NumPy error is gone. It doesn't happen out of Google Colab, but sometimes happens in Google Colab. So if you encounter some NumPy error, please try to do that runtime restart. So then, yeah, welcome back to the tutorial about our Keras graph convolutional neural network library that we're developing, as I said earlier, in our research group. I would like to walk you a bit through how to use that library, particularly to simulate molecules. So in the question, this would be task 2. So we're looking here at the data set now today that contains a lot of different geometries of the same molecule, and then we train a machine learning model to predict the energies of these different geometries and then also the forces in order to then run short MD simulations. So we also show how we can interface that machine learning library to the ASE simulation package. The main developer of this library is Patrick Reiser, postdoc in our research group here. So if you have any technical questions, also please feel free to reach out to him. Everything can be found on GitHub. You see the links here. Documentation you can also find. So please feel free to try it out yourself. I can, of course, only show a small aspect of the library here today, but there's many more things, many more models, many more application tasks that we can cover with the library. So let's start here. If you're using Google Colab, depending on your subscription and so on, you will have different GPUs here. You can connect to a GPU if you go to manage session, sorry, not manage sessions, but change runtime type here. You can use what type of CPU or GPU or whatever you want to use. So if that works well, you can test it here with that field. So you can like check what type of GPU you actually have access to here right now. And yes, then we need to install the relevant libraries here. So the relevant libraries that we need here today is actually more or less just the KGZNN library to set up everything. To visualize everything, I use this Py3D which is very nice to visualize molecules and also trajectories here in Jupyter notebooks. So the first cell, if you run this, will just install the relevant packages so we can use everything here. This should take a couple of seconds, maybe a minute. So I will already start going here further until this is done. Okay, it's already done. Then, of course, we need a TensorFlow, we need NumPy, we need some time for timing, we need some matplotlib to plot some functions, and the Py3D in order to visualize the results. Then what I'm also doing is I will show you how to train a model later. But as we don't want to train and wait until the model is fully trained, I will also show you how we can save and also load trained models. And I already have a fully trained model in my Google Drive. That's why I'm here basically importing my Google Drive. This will not work for you, of course, so I'll tell you later when to skip a certain line of code. So I will show you how to train the model, and then I will basically load a fully trained model from my drive, and you can just skip that step later. And now we want to have a model that, as I explained earlier, can do energy predictions, because the force predictions, once we have the energy predictions, are basically for free, because we can think about our machine learning model as a fully differentiable version of a function that produces E as a function of the coordinates that we use as input. So if we have a fully differentiable function, we can exploit it, we can get the derivatives with respect to the input coordinates, so we can get basically the forces once we have a trained model for the energies. And then, of course, what we need to propagate a MD trajectory are the forces and not the energies. The nice thing we can do here is that we can train our machine learning model not only based on the energies, but also based on the forces. So every time we do a forward pass during training, we can also compute then the derivatives, meaning the forces, and we can compare both the energy predictions and the force predictions to whatever values we have tabulated in our data set. So if we have a data set, excuse me, if we have a data set that doesn't only contain geometries of molecules and the energy labels, but also the force labels, then we can have two loss functions here for our machine learning model. One loss function, the traditional one, that compares the energy that is predicted by the model to the ground truth energy that we have in the data set, and an additional loss function here. And they are both now weighted with alpha and beta, that compares the forces that are predicted by the model using that differential, that derivative here, comparing to the ground truth forces. And of course, we can just, for example, use the mean squared error here as the loss functions. We just directly compare the mean squared or mean absolute error here in this case.
Can I make a quick question?
Yeah, sure. Very important. Please feel free to ask questions anytime.
From your experience, how much sensitive is this kind of model to these alpha and beta weights for the two loss functions? So you need to somehow turn in this before, or how you get this?
It's a good question. Maybe Patrick can comment on this. We are typically using a larger value for beta than for alpha. In principle, there's like, it's not a trade-off. I mean, both should lead, I mean, both loss functions can be exactly zero at the same time if we have an optimally trained model. So there's not like there's no trade-off between alpha and beta, but I think from experience, it's a bit more efficient to train with a larger beta than alpha. I'm not sure if we systematically tested this. Maybe Patrick can comment if we did or not. But typically we have beta like something like between 5. Sometimes I saw that it's much larger, like 20, compared to alpha, which we typically set to 1. But I think there's no ultimate, it's not a very important hyperparameter in my experience.
And in this type of models, the units are also important. I mean, you need to train in a specific unit, because I have seen that some of these kind of like local descriptors, they have some internal hyperparameters to define a cutoff region, for instance, or something like that. And then if you go to angstrom or Bohr, it makes a difference.
Yes.
So
yeah. If you have other hyperparameters, for example, in the Schneid representation, we have a hyperparameter for the initial embedding, which is a cutoff radius. Then, of course, you have to make sure that like this is a physical cutoff radius, so also your input coordinates should be in that unit. The other thing important is that like basically the energies and the forces are in the same unit system. So if you have energies in electron volt, you should not have forces in kcal per angstrom or something like that. So that should all be consistent, otherwise it doesn't fit. It happens a lot that there's some errors caused by wrong units here. But yes, of course, if your model has hyperparameters that are physical distances, then the actual inputs should be in the same unit.
Okay, thank you.
So we're using here in this notebook now the Schneid model that I mentioned earlier in one of the answers. This is also can be seen as a graph neural network. So we have blocks where basically we don't have message passing steps. Those are the atom-wise steps here. And then we have blocks where basically interaction between different atoms is happening, and the node representations get updated also with respect to the neighboring nodes. So with these interaction blocks here are basically like similar to the message passing steps in a message passing neural network. And this net model can be very easily accessed here using the KGCNN library. So what we have is that KGCNN, the literature that contains a large amount of different graph neural network flavors that are published in literature, and we can just import the net model. And of course, every model needs a certain set of configuration parameters, hyperparameters, and we also provide those that are provided in the original publications, or those that are basically determined by us in order to really reach the accuracy that was reported in the original publications. So I will not go through all the details here, but you basically find all the hyperparameters that are mentioned here, like for example, these embedding sizes, you will also find in this config file. The only difference is instead of using 64 as an embedding size, for example, we use here 128. So it's slightly different hyperparameters than in the original publication, but this is basically describing the whole SNET architecture. So with that single cell, we can basically make a relatively simple SNET model based on these hyperparameters. And then the SNET model is meant to only produce either atom-wise properties, for example, one energy per atom, and then you can sum over all the atoms in order to get the total energy of a molecule. Or you do a sum pooling before you do the prediction, and then you predict some molecular properties like a HOMO energy or so on. But it's not easily, or it's not initially meant to also have these derivatives. So what we implemented here is this energy force model wrapper, basically, where we can put in any energy model, and then automatically it will also do the derivatives and produce the forces as outputs. So this is fully compatible. So if you have a model implemented in KGCNN, for example, a SNET model that does like just an energy prediction, you can wrap it. So we made this energy model here. We can wrap it with the energy force model in order to have both energies and forces. And this is typically, I think, where this NumPy error is happening. So if you get a NumPy error here now, then just restart the runtime, please. So now we have a model. If we want to look at details of the model, of course, you can now go into that library and see how the model is actually set up, and then you can like make a similar model or modify this and change the number of layers here using either the config file, or you can change even the architecture of the model directly using the model here. So this should be as user-friendly and adaptable as possible. So now we have a model. Of course, we also need data to train the model on. And we also have here in the KGCNN library a lot of different data sets that are used for benchmarking purposes. And one of these data sets is the MD17 data set, which contains a couple of trajectories, MD, as the name says, MD trajectories of a couple of small molecules. And we are picking here a sub data set, which is the ethanol data set on CCSDT level of theory. And we are using of that data set the energies and the force predictions. So we can load that data set here, and this should work. And then we see, okay, this has 2,000 entries, 2,000 different conformers of ethanol, and every single conformer of ethanol has, for example, a geometry using here the Cartesian coordinates. It has an energy, a force. It has information about what are the nodes, so what are the elements here. It has a name for the molecule and so on. So there's a couple of different information stored in the data set. And we also see what is, for example, the minimal energy, so the kind of the global minimum of ethanol that was found during that MD simulation. So we can just use that data set, get all the energies, and look at the minimum of that. We can, of course, also plot that. And to plot that, I'm now exporting basically coordinate arrays as XYZ files. And I'm doing that for our data set. So these are just two functions that can convert this. So I can say, for example, the first or two random molecules out of the data set in this dataset 20.xyz file, and I'm choosing XYZ files because this is nicely compatible with this 3D Py3D viewer. So this can just load our XYZ file that we just saved and visualize all these molecules. So what we see here is now different ethanol geometries that are in the MD17 dataset. Yeah, you see there are like different rotation states, different distortions of the molecule, and this is now used as training data for our model. So now a quick question. How many of you are actually trying to do it yourselves while I'm explaining it? Maybe just quickly send a message in the Slack, in the chat here, if you're doing it live here with me. Okay, only one person, I think. The data set, I mean, there's a website that lists a lot of different data sets where you can just download them, but basically they're here in our libraries. You can also export them here from our library and save them in some format to be reused. But I don't have the link right now out of my head, but there's a library that collects a lot of data sets like the QM7, QM9, all the MD data sets and so on. Maybe Patrick, you can also post a link if you have it to the library. So for those of you who are trying to follow, are you already with me, or do I need to make a short stop here at this point of time? So are you already at the visualization, or did you encounter some errors? Just type in the chat. Okay. I hope you're not too far behind, but I think until that point, it should hopefully run without big problems. Okay, I'll wait maybe 20 seconds and then we can continue.
Meanwhile, I can just make a quick question. If
Yes, sure.
That idea of explaining the results of the graph neural network could be also applied in this case of a single molecule data set. If you want, let's say, to...
It's a bit more tricky here. We thought about it, but we didn't find a good solution yet. So this is mostly meant for data sets. We have lots of different molecules with different labels rather than lots of different geometries of the same molecule. It would be actually interesting to see, I mean, we'll think about it more. I mean, I didn't find a good solution to that yet, but it might be, there might also be interesting insights to what makes like lower than expected energies, or I don't know.
Especially in the case of non-adiabatic dynamics, because you have the hopping geometries that normally are somehow different from the others. That's close to conical intersection.
But that would make more sense if you get an explanation on the whole data set level, like what makes a conical intersection, rather than, okay, this is a conical intersection, but yeah, okay, maybe why is it? I don't know. I'll think about it.
Okay.
Okay, I just read on the chat. So yeah, it's quantummachine.org. That's what I was searching for. Quantummachine.org lists a lot of different data sets. There was a question: is there any advantage of building the model from scratch rather than starting from, say, SNET architecture and tuning it? Depends on what you want to do. If you want to develop like a new fancy graph neural network architecture, of course you want to have full control over all the layers, all the blocks that you use. If you rather want to just use a architecture that proved already useful in benchmark tasks and apply that to your data set, I would rather go on the high level and just do it as we did here in the tutorial and import basically a model that exists and configure it, and maybe then fine tune it in the end to have a parameter optimization, but not touch the model architecture itself. But it really depends on what you have in mind. If you want to like try out different new layers or like have a more complex architecture, then you can go one step deeper and basically design your model yourself. So both should be possible here. Okay, but then let's continue. So we have the model now, we have a data set, and now we want to split the data set in order to have a train and a test set. And in these data sets here, we already have predefined splits. So the model here already had information. If I'm going back, no, I don't see it here right now, but I think there should be information already in the data set about which one should be used for training and testing, because that just makes it more comparable if multiple people and multiple groups are working on the same data set. So what we do here is we get a train and a test indices and then split the data set according to these indices here. And now one important last step is the scaling. So if we now look at the labels that we have, and here I'm just plotting a histogram of all the energies that we have in the data set, then we see this is a wide distribution centered at like minus 4,200 electron volt. And this is not typically not good for machine learning models to be trained on. And this is even more tricky if we don't have that type 2 data set where we have lots of different configuration of the same molecule, but the type 1 data set where we have lots of different molecules, because then the distribution is even wider. And in order to scale that, we here implemented this energy force extensive label scaler, which is basically taking care of that. So it's trying to reduce a very, very wide distribution of energies by just fitting atom offsets, like element-specific offsets to the data set in order to shrink a very wide distribution of energies, possibly spanning multiple orders of magnitude because the molecules have different sizes, to a nice, more or less approximately Gaussian distribution. So in this case here, we don't have a that wide distribution. It's like, I don't know, 1, 2 electron volt wide, but it's centered at a very bad offset. So if we now use that scalar and then transform our data set and plot the energies again, we get something that's nicely centered around 0, roughly with a width of 1, which is much better to train machine learning models on. And of course, then what you have to do is do your predictions and then scale back in order to get your predictions again back in electron volt or whatever unit you want to have them in.
How the scalar work for the forces? You do that for per atom or? For
the forces have to be scaled in according to the energy. So what we do is we fit the scalar to the energies. The offsets don't matter for the forces, but of course, if we scale if we have like a multiplicative scaling, then this has to be also applied to the forces. Because if we basically squash that distribution, that means we're squashing the potential energy surface, and that will also squash the force vectors. But the offset doesn't really matter, because if we offset the potential energy surface from minus 4,000 to 0, the forces don't change. So we need to take that into account. But of course, it has to be fitted once to the energies and then applied to the forces, and not fitted independently to energies and forces.
Okay, thanks.
Okay. Now we still have a data set that contains basically the Cartesian coordinates, more or less, and we want to apply that to a graph neural network. So what we need is we need to basically translate that data set in one step from the input that we have to the graph tensors that we need. And this is done here. I will not go into details here now, but basically it just does a transformation. So we directly transform from the labels and the configs that we have to training and test data. And now all we have to do is basically compile our model and train it. So we need to decide how do we want to train it. We use here the atom optimizer. We choose a learning rate. We choose what are the loss functions. So we need a mean absolute error for the energy, and we have this ragged mean absolute error for the forces to be more efficient. And then here's the alpha and beta weights that we discussed before. So I set them to 1 and 5 here. But I think Patrick commented already earlier in the chat what would be things to consider here. So we're compiling the model here. This should not take long. And then the last step is to train and fit the model. And here I'm now choosing to only fit the model or train the model for 100 epochs in order to save some time. The model that I will load later has 1000 epochs, so it's trained 10 times longer, which will take approximately here on this GPU roughly 20 minutes, I think, for that data set. So it's not super long, but it's a bit too long for this tutorial here. We're also using a learning rate scheduler. You can use callbacks as you would also do in other TensorFlow models. We use the training data for fitting and then the valid test data here for validation. We use a batch size and so on. We can just choose that. And then in the end, we plot the history. So I'll start that now, that cell. And this will, as I said, take a few minutes for the 100 epochs. And I hope this also runs for you within a couple of minutes. So I'll just let that run in the background and already explain a bit further. Or maybe I'll give you a minute that you can catch up here to that point. And I see from Johannes Wasmer, that weird NumPy problem. So I hope if you click on here, runtime, and then restart and run all, you should immediately get the same thing.
Pascal?
And without the error, yes.
Does this model has any kind of regularization implemented internally for the SNET model, or like, I don't know, maybe drop out or?
That I have to hand over to Patrick. I don't know if there's regularization included. I didn't see it here in the setup, but maybe Patrick can comment on the chat if there's regularization included. But I think if you want, you can always add it. Patrick, I'm not sure if you heard the question. Does SNET have regularization built in automatically using that config file or not? Yeah, maybe you can answer later. No, okay, so there's no regularization. I mean, with that size of data set here, I mean, it's 5,000 geometries of a relatively small molecule. There's not so much risk of overfitting. And we'll see in a couple of seconds when we're approaching the 100 epochs how the behavior of the training looks like. Of course, if we now want to do predictions, as I said, I'll just let that finish now. We need to always inverse transform. So what we do is we inverse transform from the scaling the predictions, the ground truth labels. And then once we do the predictions using model energy force.predict on the test set, we also scale these predictions back. So we can directly plot them in the end using the original electron volt scale rather than the scaled units or unitless things. So we're in epoch 37, so it takes still some time. It's a bit slower than I expected today. But I already had some problems with Google Colab in the morning, so it seems to be not that fast today. And now I can already comment a bit. So these two lines you can use to save the model. So you can basically save the model itself if you make some directory in your Google Drive. Oh, someone has a faster GPU than me on a epoch 50, so it's the same roughly. And you can also save the weights, and then you can also load them again. But I would recommend you to just skip this loading step, because of course you don't have a loaded model here in your Google Drive. So just skip these two cells, and then you can do everything based on your model that you're training here with 100 epochs. And you can continue with the work with the notebook, but of course the model that was trained with 1000 epochs that I'm loading here is slightly more accurate. And maybe it might happen that when you run MD later in this tutorial, your molecule might break apart, which hopefully doesn't happen in the notebook that I have here. So we're at epoch 65. Who's faster than that? Maybe some of you were lucky and got a better GPU on Google Colab. Yeah, 70, so it's almost synchronous. Okay, Johannes, you had to restart and you're already at 50, so that's also good. So it didn't take that much long to get there. Maybe we use that time now if there's any questions right now, up to now. So on the chat, I hope you saw the answer. You can relatively simply add regularization if you want to do that, but it's not used by default.
I just have one more that came to my mind.
Sure.
In this package, is it possible to I mean, you have flexibility to define the loss function as you want. You can create only the forward pass, and then you have the flexibility to create your own training loop, or you always have the fit inside the package.
Not sure if I understand that question. I mean, you define your model inside our library. You define the forward, and everything else is done by the library itself or by TensorFlow. I mean, all the backpropagation, everything is done itself. So you don't need to do that yourself. Okay, no, it's because I just have in mind that, for instance, in the case of Torchani model, you can define only the forward pass, and then you do the training loop like for I in a number of epochs, and you define the loss function as you want. That's one of the differences between PyTorch and TensorFlow. PyTorch gives you a bit more flexibility in defining that these two loops, like the loop over the epochs and the loop over the batches. TensorFlow kind of hides that part, so you actually only have that oh, it's finished training. I'm coming to that in a second. So you only have that model.fit, but using the callbacks, you can basically do any manipulation in between. So in every single epoch, you can also do changes. For example, you can apply this learning rate scheduler that changes the learning rate in every epoch. You can do plot functions. You can do anything in every epoch. So you still have that flexibility, but it looks a bit different than what you're used to from PyTorch, where you basically make that fit function yourself. Okay. But in principle, you can do anything in both libraries, but it will look a bit different. I see. Okay, so our model is now trained 1000 epochs, and we see, okay, the validation loss for energies and forces is going down nicely, so it trains nicely. It would probably benefit from training longer. I don't know why it's plotted twice. So now we can scale everything back here and then do the prediction now on the test set using the trained model. And then we can plot everything. And then we should see a nice scatter plot between predictions for the 3 different force components here. So we only compare the actual forces to the predicted forces, not the energies. And we see that this is very, very nicely centered around the red line, which would be the perfect agreement. And we have like something like 60 millielectron-volt errors in the force components. And now, as I said, you can save and load your model. Please don't do that, because this will not work in your case. This will just lead to an error. But I'm now loading a pre-trained model from my Google Drive and then just do the plot again with that pre-trained model. And the only difference here really is that I trained it more for 1000 epochs earlier today. So the only thing is that it was trained longer. So if we now do the predictions again and then plot again using that model, we get even slightly lower errors. So after 1000 epochs, you will have something like 10 millielectron-volt rather than the 60 millielectron-volt that we had here. So this is just like, I don't know, 5 minutes training versus then 50 minutes training. And this is then more or less converged. So if you don't have more training data and you don't change the architecture, then you will not get much better than what you have after 1000 epochs here. So now we have a nice force and energy predictor. Now, as I said in my talk, we can use that now for running MD, running molecular dynamics. And for that, we interfaced, or we wrote some interface between the KGCNN library and the ASE environment. So we can use all of the tools that are already implemented in ASE in order to run ND trajectories. And for that, we need to basically set up a couple of things. We need one dynamics model, which is basically like the interface between both worlds. So in every single MD step, what has to be done is we basically use ASE to update the geometry according to the forces and the thermostat and all that. And then we have to basically do some graph pre-processing that basically goes back from the geometry to our graph input that is needed by KGCNN to make useful input for KGCNN. And then we need to do a forward pass in KGCNN, and that is done using our trained model energy force. And then we do some post-processing that basically goes back from the output of KGCNN and translates it back to what ASE needs in order to make use of the forces. And this is basically just the rescaling of the forces. So we have here this dynamics model, which is basically just wrapping the pre-processing, the forward prediction, and the post-processing in one nice model. So just some setup here, you don't need to do a lot. And then what we can do, for example, is we can run very simply a geometry optimization. So what we do is we pick a random molecule, in this case the 0th molecule here, from our data set. We take the Cartesian coordinates, which are stored here in Z. Z is the atomic numbers, and R are the Cartesian coordinates. And we initialize an ASE atoms object with that information. So this is atoms object contains the first molecule of our data set. And then what I do is I just run a geometry optimization, meaning I, in every single step, ask our trained model, what is the force acting on that molecule? So what is the gradient? And then I go in negative gradient direction in order to go down the gradient and find the minimum of that molecule. And to make it a bit nicer to illustrate, what I do is I apply a random distortion in the beginning. So I start with the coordinates that are stored here in this atoms object. I add a random distortion here. This is just Gaussian noise. So the molecule is a bit more distorted, a bit slightly higher in energy. I add this distortion to my coordinates, and then I just iterate. In this case, I do 50 iterations. And in every step, I set the coordinates of my atoms object to the current coordinates. I convert this to a graph. Then I apply my dynamics model to that graph to do a prediction. Then I just look at what is the predicted energy, and then I save that to my trajectory. I also keep what are the elements and the energy, so I can plot everything later and visualize it. And then I do the update. So I look at the force predictions. This has an index of 0 here because we can do multiple predictions at the same time. We just feed one molecule here, so it's just predicts the 0th one. We ask the forces, and then we update the coordinates accordingly. So let's look at what happens. So we do this. We run 50 iterations, so we should see the output in a couple of seconds. Okay, so we see, okay, it's doing its steps. In every single step, we see the energy, and we see that the energy basically starts at a relatively high value. I mean, high in terms of that value in electron volt, minus 4,206, and then it relatively fast goes down to converge here at this final number here after 50 steps. And now we can look at the energy as a function of iteration steps. So we see, okay, it converges. So the energy goes down and then saturates. We can export again our trajectory, both the coordinates and the elements as this XYZ file here, and look at what actually happens. So if we zoom in now, what we see is it starts with a slightly distorted geometry. This is a bit slow. Maybe it makes that faster. So we see that it starts with a strongly or slightly distorted geometry and relatively fast goes to more or less equilibrium geometries with a nice tetragonal carbon here, the correct angle for the OH group and so on. So we can see, okay, this is very nice. We can use the force model to minimize the energies here. Now, as I said, last step would be now, how do I go to an actually MD calculation? So what we use is the ASE calculator object here, which is basically now doing the conversion and the dynamics model. So it's again a wrapper that directly then can be used in ASE. So we use for the atoms object as the calculator, we use now our KGSNN single calculator, and then we can just use, as we would usually do in ASE, pick a distribution of initial temperature and velocities, use a thermostat, and then we can run that thing. So we define that here. We want to have a function that prints the energies in every single time step. So we define that function here that tells us what is the potential energy, kinetic energy, and total energy here. And then we can just basically, again, do a loop, 200 time steps of MD. We want to save everything in these empty lists here. And in every single time step, we just run our that dynamics object here from ASE using that thermostat for one time step or 1 femtosecond. I don't know what the one exactly represents here. So if we run this, we'll see that in every time step here, we will now get very fast the energy per atom, kinetic energy, total energy, and so on. So 200 time steps is done very quickly here in a few seconds, which would take, of course, much longer if we would do one DFT calculation in every single time step, yet along a CCSDT calculation. And now again, we plot the energies, potential energy and total energy and kinetic energy as a function of the 200 time steps, and we see total energy is more or less constant, and we see more or less oscillations that are in different directions between the potential energy and the kinetic energy. So as we expect, we will have some transformation of kinetic to potential energy and back during our MD trajectory here. And of course, we can also visualize this, and this is the last step here. So we save everything again as a trajectory, a XYZ file, and again look at the visualization of that. And you will now see, hopefully, a nicely wiggling molecule here that is generated using the ASE calculator. So I hope with this I gave you a good overview of how we can use all the functionality of the KGSN library to train on data sets. Also, of course, if you have your own data set, we have all the converter functions that read a given data set in a given format and translate it to the data set format that we need. If you have questions about how to do that, again, feel free to reach out to us. So you can also train it on your own data sets. And then I showed you how we can now train the KGSN models. Of course, you can not only train the SNET model, but also other models that we have implemented, some of the equivariant neural networks, some of the invariant neural networks, and so on. And then I also showed you how we can interface that directly to molecular dynamic simulations using ASE. And with this, as I said, I'm at the end of this short tutorial introduction. I hope you can use that tutorial to spend a bit more time playing with it, trying to adjust to parameters, train shorter, train longer, play with the ASE. If you have any questions, here's our contact details. So reach out to us if you want to use the library, if you have questions how to do something, if you encounter some difficulties. Also, feel free to suggest changes on the GitHub repository. And with this, thank you for your attention. Thanks for Patrick for answering all the questions on the chat. I'm stopping the screen sharing now, and I'm happy if there's more questions or more comments to answer. So thanks a lot for listening.